On July 16, 1945, a nuclear weapon was detonated for the first time. A few miles away, the physicist Enrico Fermi was dropping shredded pieces of paper to the floor. Based on the motion of the paper, Fermi was able to estimate that the force of the bomb was roughly equivalent to about 10,000 tons of TNT, a number that ended up being surprisingly accurate given the limited amount of information that Fermi was working with. If you're anything like me, you're probably wondering, how is this even possible? Luckily for us, we don't need to become legendary nuclear physicists to find out. A Fermi estimation is a rough calculation which aims to be right within an order of magnitude or factor of 10. Rather than being extremely accurate, Fermi estimates prioritize getting a good enough to be useful answer without investing large amounts of thought and research. We can use Fermi estimation techniques to answer important questions like, how long would it take for everyone in my county to be vaccinated against a new strain of influenza? How much would it cost to fill my entire school with popcorn for my senior prank? Or even, what is the probability that life exists on other planets? Let's do a quick example. How much does the New York State government spend on K-12 education every year? The first step is to break down the problem into smaller, more manageable chunks. If done correctly, this will allow us to use knowledge that we do have to make estimates about things that we know nothing about. Furthermore, the more subcomponents we have, the more likely it is that our over- and underestimates will negate each other, giving us a more accurate final estimate. In this case, we can start by estimating the total number of people in New York. I know that the population of NYC is around 10 million. This gives me a good lower bound, or minimum estimate. I can also be fairly confident that the total New York population is less than 50 million people. This will be my upper bound. At this point, my intuition says to simply use the average of these two numbers for my estimate. However, we are actually going to use something called the approximate geometric mean. Instead of calculating the number in the middle of my upper and lower bound, the geometric mean calculates a number that is an equal number of factors away from these two numbers. This is a more useful value in Fermi problems, where our goal is to estimate a number within an order of magnitude, or factor of 10 of the actual answer. To find the approximate geometric mean, we simply put our numbers into scientific notation and take the regular average of the coefficients and exponents of our upper and lower bounds. This gives us an approximation of 30 million people living in New York. From here, I can take a guess that about 1/6 of the US population is within the K-12 age range. That's about 5 million kids in New York. I would guess that most teachers get paid about $60,000 a year and that there are about 30 kids in a class. If there are about 3 general staff members for every class of students, that gives us about $6,000 spent per child per year on staff salaries. However, I also note that there are a bunch of other factors that go into running an education system. Buses, buildings, books. Fermi estimates are all about speed and generalization. So instead of trying to individually calculate all these costs, I'm going to guess that it all comes out to about a few $1,000s per student. Adding this up, it gives me a total of about $10,000 per child every year. Using this estimate, we can conclude that New York spends about $50 billion per year on K-12 education. All in all, Fermi estimates are a simple yet incredibly powerful tool that can help you improve decision-making across every area of your life. It's also a pretty neat party trick. I hope you give it a try.